Okay, this how-to webinar is going to cover some of the differences or some of the features that are available inside the Allegro and Allegro with high-speed options that are available with the Cadence PCB tools. So I would need, when I go to File and Change Editor, I would need at least an Allegro PCB Designer license and then the high-speed license as well to be able to cover a lot of these features. If we actually have a look at the parallel-systems.co.uk web page, there's a webinars, sorry, not a webinars, there's a matrix option on here. And if we scroll down here, we just these are all the features that are available to the differences between kind of an OrCAD Standard, OrCAD Professional, and Allegro PCB Designer. These are kind of YouTube links, so lots of video links all the way down here. And if we kind of scroll down towards the bottom of the matrix, you'll see obviously we start to get into just the features that are available inside Allegro, and then you've got the PCB high speed option. And this video is going to be covering kind of a lot of the features like delay tuning, phase tuning, remove tuning, the timing vision, etc., and some of the high-speed via structures and differential pair options that are available with the high-speed license. So it's worthwhile having a look at kind of the matrix just to kind of work your way through these. And there are individual kind of video links on these again to click on and see how to use these specific features. Okay, so we're going to start off with a board. We're going to start off with timing vision and auto-interactive delay tuning. So in this scenario here, I've got a match group, a little DDR memory. So if we go to Constraint Manager, and I look at my my routing and my relative propagation delay, I've got a match group here, the DDR DQ. And what's happened here is that I had the bus, everything was delay tuned and meeting all the constraints. So if I just go and show you what the routing looks like. So it's kind of this bus area in here. You can see it's all been lead tuned and matched. Everything was great, and then the chip manufacturer gave me an updated pin delay file, so the difference from the bond to the pin, and what that did is that made some issues, so I've now got some constraints that aren't meeting. So you can see obviously I've got some reds and greens, and what I want to do is go and delay tune these quickly. Now I can obviously have Constraint Manager open and try and cross-reference Constraint Manager and work on the ones that I need to using the DRC system, but by using the timing vision, what this does is physically cover the C lines or the tracks to meet the constraints that I've got. So if I actually go to the root and timing vision command, and then we look at our options pane, we can obviously have green would satisfy, which means it's meeting the constraint, yellow would be too short, purple would be too long, and I've got kind of a pattern for what they class as the target value or the critical signal. I've got some different modes, so I can work on DRC or smart timing and DRC or smart phase. DRC timing and DRC phase physically look at what the constraint is set at. The smart phase and the smart timing look specifically at all of the match groups in the design and what their length requirements are. So if you've got a clock, for example, that's going to be available in multiple match groups, instead of kind of doing one match group and then going to the next match group, and you end up kind of chasing your tail going around, making an adjustment to one, and you have to go back to the original one because you've pushed that value too long. This actually takes a lot of that into account and may add values or length to those to allow you to kind of work on a smart basis. So what we'll do is we'll pick smart timing here. I've got match group selection mode, so I'm going to pick one of the members, and then it would then highlight all of the match group. So you can see I've got some that are green and some that are yellow. So some are meeting the constraint, I've got some that are too short. Let's just do a quick update of the goals just to make sure I'm up to date with the latest values. And I can then zoom in, and if I start to hover over these C lines or net members, you can see that I get the tooltip is taken over and I get a lot more information about this specific match group. So if I go to this one, it's telling me that it's too short, and it's too short by a specific amount, and I need to add some delay. So again, I can do this manually. I can just use the root command and maybe just try and root a little segment in here. I can use the manual delay tune command and manually to do this, and the track value will update as I'm going along. So or I can use the auto interactive delay tune command. So let's get the tool to do it for me. So by using the auto interactive delay tune, again, high speed license, I can actually get this to actually do all the work for me. So I can literally just change some values here. We've got different settings here, whether we use an accordion or a trombone. And you can adjust the settings to how you want when you're doing your delay tuning. And I can then just window a couple of the tracks, and you'll see it effectively has the little bump in for me. The C line changes to green, which means it's meeting the constraint, and I can then move on and work my way down. So let's just zoom in here. We'll just maybe window select a few of these. So you can do these as a whole bus. You can do these as an individual section. You can do them one by one. It's entirely up to you how you kind of handle this. But it's giving the tool a chance to be able to fit it all in. So, you know, I've done that one there. I haven't got enough room. Still not got enough room, so I'll leave that one for now. We'll come back to that one. Let's just do these individually ones quickly. Maybe try and give myself a little bit more room to see if it can push these out. Still not working, so maybe let's just adjust this. Let's just manually bring this track out, and then just manually add some values here. And then if we did the root auto interactive delay tuning command now, just tidy this up a little bit. Yeah, okay, we're meeting the constraint, that's good. We can then move on very, very quickly all the way through the bus. So I've still got this one specific one here. Again, you can do this manually. We can also use another command. There's one called remove tuning that will physically remove the tuning for me. Maybe let's just tidy this up a little bit more. Just slide these out. That's okay. Let's try the root delay tuning now to see if we've got enough room. Yeah, we have. We're meeting the constraints. All the bus has gone green, and I can then move on. So very, very quickly, just by using a combination of kind of the auto interactive delay tuning, the remove tuning, the manual delay tuning, the manual routing, you can use the timing vision to see the color of the tracks, and you can very, very quickly work through the match groups and do what you need to do. So let's just turn this timing vision off for this one. So we'll just clear the selections and done. Okay, so I'm going to show you the auto interactive phase tuning and timing vision. So on a differential pair, for example. So I'm just going to turn on the bottom layer, and I've got a differential pair here. So again, if we use the root and timing vision, let's look at our options. So I want to do effectively smart phase. I don't want to match group. I'm just going to pick effectively one member of this differential pair. So you can see from a routing point of view, actually, you know, I've got one that's too short and one that's too long. I'm looking at both of these, working my way through where the net is. I can manually adjust this again, so I can add some phase bumps using the phase bump command, or I can just use the root auto interactive phase tune command. This will physically shorten the pad entry. It can potentially lengthen the pad entry. We could add off angle segments. We can adjust the gather move, or we can just add some uncoupled bumps. And if I look at the options, these are the options I can add which kind of size of bumps that I want to add. Let's just cancel that. So using this command, I'm just going to say, let's go and add some uncoupled bumps. Window select the two halves of the differential pair, and it adds some phase bumps into this. Obviously, these become a little bit more uncoupled, so which is more important to you, whether they're uncoupled or whether they're matching in length. But that's the decision that you can make yourself. But the tools, auto interactive phase tuning and timing vision, allow you to very, very quickly resolve these kind of issues. Let's just turn the timing vision off. So let's clear the selections, and we can then move on to the next section. So routing differential pairs. Let's just go back to the visibility pane. We'll just show all the layers. So sometimes it can be key when you're routing a differential pair that you want to add a set of return path vias. These can be associated to a ground net or the associated plane with the differential pair. So when I'm routing a differential pair, for example, and I've got a little differential pair just routing here, I can obviously just do a double click to add the vias that I need, but with the high speed based license, I've got this return path vias option, so I can actually just have a look at the settings. That's from a right click. So you can see obviously I can assign the net name for my return path. I can pick a pad stack for the return path vias, and then if I look at the spacing options, I get different options. So I can add just a single via, some inline vias, some equidistant vias, offset, diamond, or rectangular. So you have different styles of return path via arrangements when you're doing a differential pair, and you can adjust the spacings as to suit if you want. And then when you're routing, literally I just do a double click to add the vias, and you can see it's add that based on the settings. So if I look at the return path vias prototype, I'm using the inline one. I could choose an offset one here for the next style, and it now gives me that offset via location. So let's just change the via pattern maybe to be vertical, and every time I effectively drop and add vias, it would then give me that via arrangement based on the return path. So that can be really helpful. These are normally manually defined if you haven't got the high speed based license, so you can save a lot of time by adding the return path vias as you go along. So that's kind of the return path vias option. There's another feature called Fiberweave. So obviously when you're routing across a section of FR4, you've got inconsistencies in the FR4 potentially. You can get some changes in impedance and in coupling. So what we want to do is maybe put maybe a stagger pattern on, or a Fiberweave pattern. So if I just show you this as an option, so root unsupported prototypes, there's something called the Fiberweave effect, and I can add a zigzag pattern. If I look at the options pane, I've got an angle offset and a max angle or a max length. So I'm just going to set 5mm. I'm literally just going to window select the tracks here. Just do the Fiberweave all the way across. I'm good to go. That's kind of my Fiberweave issue resolved, and I can then work on. Let's just change the visibility again. We'll just go down to a single layer. The next option is adding tab routing, and what this does is effectively, again, for an impedance and coupling issues, you can add effectively a little shape bump to all of these traces that can help you just try and make these traces more coupled and more matching from an impedance and coupling point of view. So again, route unsupported prototypes, there's an option called tab routing, and we can generate tab, we can move tab, we can delete tab, and then we can do an analysis. So we'll do a generate tab option here. So I can effectively add some values in here. So let's just set these up as 0.2, 0.3 for the width. And you can see the graphical representation here showing me where the tabs are going to be added. And this is just setting up the sizes. Let's set that 0.1 and maybe a millimeter. You've got different options to whether these are going to be internal in a BGA region. This is just an external routing, so I'm just going to do the interdigital one. The help button here is really useful because it will actually go through and give us some options and give us some descriptions. So I can then effectively then just draw a window around the options that I want, and you can see that these little shape bumps get added to the tracks as I go along, and I can just pick different C-line segments and try and get some consistency and some matching on the tracks that I've got. Once I've done that, obviously I've got the options to move the tabs. So I can use a route tab weave, and there's a move tab, there's a delete tab to work the way. We can also do an analysis here where we can build rules based on the nets that we have to make sure that we're meeting the number of tabs on each track so that they're all consistent. So this next part again is an inductance improvement or an impedance improvement, and it allows us to add an L comp based structure around this specific pad. So let's just turn the layers off. So if I did to the root, there's something called a structure, and we can create a structure here. So there are high speed via structures, so we can create via structure fan outs if we've got differential pairs coming out specifically of a BGA, for example. I've also got options to create things like an L based comp, which will give me this specific shape, a loop going around the specific pin, which can help me control impedance on a track. So what I'll do is I'll start off by picking the pad stack that I want to use, and you can see it then populates the pad stack. I pick the trace layer that I'm interested in, and I start to populate some values. So the track width is 0.2. I want 0.2 as a clearance. We'll leave the loop angle. I want a void shape, so we can actually get it to automatically create a void shape underneath this. You can see kind of there's a version of this shape underneath here, and I can then say let's maybe use the ground and in a 1 to create a root keep out area specifically underneath this. Once I'm happy with this, I can then go and generate this, and then that option is then attached to my mouth, and I can then go and effectively select the pin that I'm interested in, and that's added the root based on the net name, and I can then join this up and use that as a via structure. If we look at the layers beneath it, so we look at the root keep out on the ground layer, you can see it's generated a ground layer there and on inner layer 1, and it makes this root keep out area so you can use that on any layers that you specifically need. The next bit we're going to go through is something called return path. So we've got some return path checks. If we go to Constraint Manager, there's now a worksheet using the high-speed license called the return path. And you can see I've got a return path group. This is just made on a class, and you can add nets to this. And then what we're doing is we're specifying effectively a reference net which reference layers we're using, and you can obviously have a closest plane option. And then we can use an ignore max of tracks and what the margin is going to be. And then there's also an option to make sure that we add a stitching via. So you can add a stitching via to the beginning and end, or every via that's on that net. You have a ground stitching via that's associated with it. You can see I've got some DRC errors here, so let's just zoom in and have a quick look. So the first one, obviously I've got a stitching via missing. So if I look at kind of the DDR data 2, I've got effectively my via here, and I've got a return path via within the dedicated area. On the next via, on this one down, the DDS data 0, I haven't got a return path via. So what we'll do is we'll just do a simple copy. So let's just copy this via here. We'll just go and place the via down. DRC disappears, you can see that. Let's just go to Constraint Manager and just refresh it. So we'll relaunch Constraint Manager, and you can see that my error for the return path via missing has gone away. I've actually got some other errors here though. Void crossing, so if I double click on here, it will physically take me to where these are. Can't see what's going on here. So there is something under the Vision Manager. So under View and Vision Manager, we've actually got something called the Return Path Vision, where I can set colours. So if it meets the constraint, the track would be green. If it doesn't meet the constraint, I'm just going to pick a red colour. Let's just then modify my selection. Let's just simplify the display again. We'll just pick these tracks. And you can see I've got some that are missing. I've got an issue. I've got a return path issue here. And if we actually turn my ground plane on, you can physically see I've got a void left in from a previous design revision. So I can obviously need to adjust this. Now this is a live link. So if we were to go into, say, shape edit mode, and let's just slide the segment, you can see this one then updates from a color point of view. These two are still involved, or these four are still involved. So it will physically update as I go along using the Vision Manager and the Vision options. So that's Return Path Vision that's available in the high-speed license. Okay, this next option, I'm going to open a different design. So I'm just going to go and open something called the ACC Start. So what we're going to talk about now is something called the Allegro Constraint Compiler. There will be a more dedicated video on this. There is also a really useful feature you can work through this. There's something called a Rapid Adoption Kit. So if we go to the Cadence Support web page, under the Resources and Rapid Adoption Kits, so support.cadence.com, and if we look under Allegro PCB Editor, you can either type searching for this, or we can just scroll down. There's one here called the Allegro Constraint Compiler. And this is a really, really useful workshop that you can work through and go through the Constraint Compiler. It kind of gives you the PDF here. We come down a little bit option. There's an option here to download the database and the labs, and it will walk you through step by step about what the Constraint Compiler is. But the basic principle is that you can actually start to build constraints based on an Excel workbook file, which can help you when you're reusing constraints from design to design, especially if you're just starting to maybe tweak net name values. So let's have a quick look at some examples. So I've got effectively some basic rule sets, so I can do things like a differential pair rule, a physical rule, and if we just open the Excel file, just have a quick look. There's a predetermined structure, so I'm going to make a rule called 100 ohm differential pair. I'm going to set the min line width, the min net width, the primary gaps, the next gaps, and the same for the spacing rule. So I want effectively set some spaces here. I'm also going to set effectively a diff pair control on this specific rule. The key part here is you then save that as a CSV file. If I look at a physical spacing rule as well, so again I've got the physical and spacing rules for that specific design. The way you run this inside of PCB Editor is we launch Constraint Manager with the high-speed license. Let's just maximize this. Under the Tools menu, there's something called the Constraint Compiler. There is an ACC library path. Let's just go and show you that quickly. So under Setup and User Preferences, under the Paths and Config, there's something called the ACC path, where you would specifically specify where you want to load these files from. So we go back to Constraint Manager, Tools, Constraint Compiler. This then gives me access to my ACC library files. So I'm going to effectively pick Lab 1 and load the selected file. And then click Next. And you can see there's my differential pair rules and my physical spacing rules. I get the option here to validate this. This then generates a constraint compiler report. So you can see effectively it's added a constraint set, an electrical and a physical constraint set. And there's a list of the phase rules. I go to the physical based rules. There's the 100 ohm differential pairs. So it's added the rules for me. And if I'm happy with that, I can then apply that specific constraint to the design. The generate report says again, we can then close this. And if I look at my effectively my routing rules, so let's look at the differential pairs, it's added that phase rule. If I look at the physical based rules, it's added the differential pair ones, the 85 ohm and the 100 ohm differential pair rules have been added to my design based on the different layers. So you can actually use this to build rules. You can actually use it to apply nets to rules, to make net classes, to make net groups, to make match groups. So this is just a brief overview. It's worthwhile having a look at the the Constraint Compiler Rapid Adoption Kit, which will work through the step-by-step instructions about what you need to do, what the basic principles are. But it's a good insight into what Allegro Constraint Compiler is capable of. Okay, the final part of this webinar, we're just going to go through some basic options. So let's just go and open a different design again. So in this example, I've got a DDR memory, an FPGA using a flyby technology. So I've effectively got 4 memory devices, and it's effectively going from the FPGA to memory device 1, to memory device 2, to memory device 3, to memory device 4. Having to build all the rules and the constraints for this can be quite time consuming, and you can actually get the Allegro with high speed option to actually automate some of this process for you. So I'm just going to open a version of this design that's not rooted. So you can see there's my unrooted board, and if I go to Constraint Manager, if I look at the routing and the wiring options, for example, I've effectively got 2 byte lanes, I've got an address control line, I've got some differential pairs, and some basic other nets as well. So not much net-wise, but no rules in this at all apart from maybe a differential pair rule. Okay, so what I want to do here is I effectively want to use the net class option to drive how I build my match groups. So you can see if I look at my relative propagation delay, I've just got classes. I've got no match groups in this already. So we can kind of automate this process a little bit. So I'm going to start off by just scheduling one of the nets. So we'll use this as a basis. So logic net schedule. Pick on any of the nets. And you can see effectively I'm just going to schedule. So I'm going to start off on the FPGA. I'm going to go to memory device 1, memory device 2, memory device 3, memory device 4. And then just complete that schedule. So that's good for me. We'll then go to Constraint Manager. And if we look for that specific net, there's a user-defined net that I've effectively scheduled. So I'm just going to take that net here, and I'm going to take it into Signal Explorer. I'm going to pick the Allegro with high speed license, and the key part with this is I actually have the ability to set constraints, and this is kind of what I want to do. So you can see there's my basic topology, U1 to U2 to U3 to U4 to U5. If I look under the set constraints command, these are the different constraints that I can set. So let's start off with maybe a wiring option. So I've got a schedule based template. Do I want to verify that schedule? Yes, I do. So I want to make sure that I route according to the schedule that I've got, and I'll get a DRC if I don't. Let's just specify a stub length. I can also add something like a max via count. Again, that's only available in the Allegro PCB Designer license. If you wanted to add total X length rules as well, you can, and specify layer sets as well. Let's go specify an impedance based rule. So all I want a 50 ohm impedance, and maybe I want a 2% tolerance on that. So I'll add that as a rule. I've got things like differential pair rules. I've got propagation delay rules, signal integrity, max parallel, switch settle rules. So you can drive all of these kind of rules if you want into Constraint Manager. I'm going to go to the relative propagation delay. I'm going to start off, I want to go from U1 to U2. So this is the first part. I'm going to call this DIM1. This is the first section. This is going to be effectively a class-based rule. So it's using the class. So because and this is quite key to get it to make the match groups automatically, we can use delay in length or time. I'm going to use the delta type in length as 0, and the tolerance is also going to be length. A millimetre is good enough, and I'm then going to add that rule. We're then going to go from U2 to U3. Call this DIM2. 0 and 1, and we'll add that one. Let's do the same. So U3 to U4. Called DIM3. 0 and 1, and we'll add U4 to U5. We'll call this one DIM4. 0 to 1, and we'll add this specific rule. So that's built the class rules that I want. So what this is going to do is look at the connections that we've got, and anything that's in that class, it's going to build a match group. So it's going to build up the pin pairs from U1 to U2, U2 to U3, U3 to U4, and work your way through. And U4 to U5, sorry. So we'll click OK to that. I can then use the file and update Constraint Manager. And you can see Constraint Manager is now flashing at me. Do I wish to associate this net with this specific net name? No, I don't. So I'm going to take this one out, and then we'll effectively just clear this manual rule here. So I've unscheduled that net. So none of them are using this specific rule again. But if I now look under the routing section and wiring, effectively there's it's called DDR-CKE. You can rename that if you want when you're making the rule. I just left it as it was. So there's my template with my stub length. If I go to the vias, there's my max via rule, there's my impedance base rule, and there's my individual dim rules as I go along. So if we then go to the propagation delay rule section, or the net section, and I'm going to apply that rule to the net class. So there's the DDR CKE. You can see there's no match groups at the moment. As soon as I apply that, it makes the match group. So dim1, U1 to U2, dim2, U2 to U3, dim3, U3 to U4, dim4, U4 to U5. So that's generated all the ones for byte lane 0. We can also repeat that for byte lane 1. And we can also repeat that for the address and control. Let's just close Constraint Manager just to reorder them, and then we'll reopen Constraint Manager. And you can see effectively there's all my individual match groups. It's worked its way through and done all the hard work for me, and just by using that topology based rule. And this is something that again is available within Allegro PCB Designer with high speed license, because you get the ability to set constraints in Signal Explorer. That concludes this webinar. I hope you've enjoyed it.